I think there is no one who hasn't pulled his hair while dealing with these line models, frequency-dependent line models. So hopefully we'll find a solution before you lose all your hair. So yeah, it is. But today my objective is to show the new wideband line and cable model, and also maybe you'll have some sympathy for us because it's a very tough problem. Okay. If we look at the line models in EMTP, this is the list. So we have pi line models. Basically, this is using lumped parameters. And then we have distributed parameters, so we can study traveling wave phenomena on lines. So we have two groups here, constant and frequency-dependent parameters. As you go from left to right, the complexity increases, and the wideband model is the actually most accurate model is supposed to be, and also is the most complex model. Why? Because here it is constant parameters model, so the RL parameters of the line are considered to be constant. But for frequency-dependent parameters, we have two levels of accuracy. In the first level is model domain. It is like consider the Z impedance matrix, and you apply transformation matrix, and you get eigenvalues or these sequence parameters. For lines, for example, if you apply transformation to propagation function, you get the propagation modes. They are decoupled with the transformation. The transformation itself is actually frequency dependent. So you decouple the modes for a certain frequency, but this matrix doesn't work for another metric, another frequency actually. So, but for lines, this is not a big problem. So FT line model usually, so FT line model is doing this, does not consider the frequency dependence of transformation matrix, but wideband model does because it is in phase domain. So we consider the frequency dependence of everything. Propagation function in phase domain. So this is how wideband model works. So the vocabulary in this business, it's we have wideband model, we have universal line model. Wideband model in EMTP is an implementation of universal line model. It is, but of course, there has been several improvements. It is not like exactly what is written in the paper. This is another problem in this field because there are many papers, and some users who want to dig, they cannot find like what is the exact implementation. So hopefully by next year we'll solve that problem too. We'll have only one. We'll have a general paper about that. And we have time domain, frequency domain, and FD line is frequency-dependent line. And also we have this new line cable model. It is called cable correction. This is frequency-dependent cable model. So the formulation is very close to universal line model, but I will explain the difference and how it solves many problems. Thanks to this, we can achieve modeling any number of conductors. There is no such tool, I guess, right now other than EMTP. So if you have 50 cables, it is okay. And then we have Statespace, propagation function matrix, characteristic admittance matrix, and nodal admittance matrix. These two things are used in actually frequency-dependent line models. So in distributed line models, the propagation function and characteristic admittance matrix, basically. Using these, you can obtain the nodal admittance matrix for steady-state studies. But basically, what we care about, these are the two things that allows us modeling a line in time domain. So what is the work, the nature? We have three outputs, like the time domain solution. This is the Wideband model coded in Fortran, but using, of course, object-oriented programming techniques. And so when you choose the wideband line model, basically the time domain solution will be this new time domain solution. And the second thing is the fitter. This is executable, coded in MATLAB, and it is an offline thing, so it is used for frequency domain system identification. So basically, we identify propagation function and characteristic admittance using transfer functions. This is what we do, okay? So, and these transfer functions are solved in time domain and actually coupled to EMTP network. So your network is connected to this line model, and there is a connection between the two. So the fitter and the, of course, we had many documentation. We explained how we do the things and so on. Some of them are available for all users. Some of them are internal documents. So regarding the existing wideband model, the fitter is based on universal line methodology. But if you have many conductors, then we have some problems. Everyone has problems. And if you increase the frequency band, it creates ill conditioning problems. Obviously, in the same matrix, you have millihertz and you have megahertz. The conditioning of your matrix is problematic. And sometimes it generates unrealistic time delays. This is due to loss factor in cables. And sometimes you have precision problem at DC frequencies. So for HVDC studies, you're doing switching studies, you want the right answer at DC in steady state, but also you want the right transient answer. So this is a little bit of a problem because your fitting system becomes really, really large band in that case, and you may have ill conditioning problems. And sometimes you have unstable models, and it just explodes in time domain. And people always say this is passivity. No, it is not. Sometimes the reason is different. Sometimes the reason the Statespace model has numerical problems. It is not balanced. It is really another field of study. If you look at MATLAB, Statespace, unstable, or numerical problems, you will find many documents or literature about this. So in those cases, of course, one solution is you reduce the time step. So to get something, so this is the number one solution, for example. Okay, the model is good, passive and whatever, but your state space parameters are not balanced. So what you do is you reduce the time step, you reduce your numerical errors, you reduce your interpolation errors or whatever. So in time domain, how do we do the solution? We have these transfer functions of the line, and I need to solve them in time domain and integrate to my circuit, right? So how do I integrate to the circuit? It's like a current source. It's a Norton branch, actually. I think so almost all models in the industry, they use either trapezoidal integration technique or Euler backward. This is the same thing for the line model. And of course, because of that, there are important integration and interpolation errors. So we had to tackle with this. So we made a solution for that too. So also there was a mismatch between frequency domain and time domain solutions. So your steady state frequency domain solution doesn't match your steady state time domain solution. And there is when you want to initialize your solution from frequency domain, you see some oscillations which are not natural at all. So we needed to have a seamless transition from frequency domain to time domain. This was one of the objectives. And during transients, we had ringing problems. And the memory allocation was huge because the array limits were hard-coded for some reason. And also, we had 5-dimensional arrays because of the complexity of the problem, and so on. So I will, of course, tell our solution and how we fixed all these things. If you look at the state space forms of the functions, this is important to see one of the contributions. This is the propagation function. So it is very simple, actually, here. Usually, if you look at papers on line models, they have 100 equations. Here, I will just show a few equations, that's it. I think these are very useful to understand what's going on. This is your propagation function. It is composed of model contributions here. And each model contribution, of course, has a delay associated with it. So you have these model contributions. Each one has a single delay. And so this is a complex system because it's a multi-delay system. In EMTP, in universal line model, here, the model contributions are not fitted individually. It is very hard to do that. So what they do is they combine everything here by finding poles, and they find the residues in phase domain with a formulation like that. So this is what universal line model does, okay? The poles, they come from propagation modes, and residues are evaluated in phase domain with this formulation, huge formulation. For the characteristic admittance, it is not complicated. You can easily find a transfer function equivalent for characteristic admittance. But for propagation function, it is a little bit of complex. So first, you find the delays by doing transformation. Then you find the eigenvalues, and from those you find the poles, and then you do the fitting in phase domain using this technique. Here, the only unknown, it is the residue matrix here. So, however, the problem with this approach is, well, the final solution is good. You know, it is your sum here is equal to this almost. Of course, there's an approximation error. So because we minimize this using least squares technique. However, the problem is if you look at these model contributions here, the thing here, and the model contributions of the universal line model, they don't match here. They don't match. Their sum is the same. So this here, the model contributions. So H in phase domain, it is the same. But what does ULM does is ULM does sort of ULM uses, the universal line model uses an arbitrary set of model contributions. The final solution is good. Let me say this way. You have 2 plus 2, okay? It is 4. In ULM, you obtain the same result, but you say 1 plus 3. Okay, that's how it works, you know. However, the thing is here, if the model contributions are unbalanced, in certain cases, this may create numerical problems. Because, for example, you have a delay group, and you have a very high residue, and you have other delay group, which is close to that one, but it is residue with negative sign, okay? This is, I'm not gonna spend too much time, but this is what it is, and because of that, you have numerical problems sometimes. This is especially true for cables, okay? So what we did, we said, okay, maybe we should fit each one of them separately. But it was not so obvious. Why? Because their behavior was not smooth. And in the world of fitting, if something is not smooth, it is very hard to fit. So then we, by observation and spending some years on it, we realized that these non-smooth behavior was due to repetitive eigenvalues. It's written in the books, eigenvalue perturbation theory, whatever. So basically, we realized that, you know, so the model contributions, you have smooth ones, and you have non-smooth ones. But the non-smooth ones were repetitive eigenvalues. So we grouped them, we obtained something smooth. So this was our magic solution. So basically, for some cases, we apply this. It is called cable correction. So if the model doesn't work, the user can choose cable correction, and he can have this nice fitting, proper fitting of each model contribution. So this has numerical advantages in some cases. So this is one of the things. So concerning fitting, I would like to add a few words. It is, well, fitting is not easy, okay, because you have a multi-delay system. So you have a range of frequency band. This impacts the fitting. This impacts the numerical conditioning. In the same matrix, consider you have a transfer function. You have 0.01 hertz, and you have megahertz to the power of something, depending on the order of fitting. So this is not easy. How many frequency samples do you have? Is it overdetermined? Is it underdetermined? So these, all these things have an impact. So the conditioning, number of conductors, and also the electromagnetic properties of the electrics, configuration of conductors, input data accuracy, which is for me the worst, because you can spend a lot of time playing with your model, but still it doesn't work because the cable constants, you push the cable constants routine to its limits, and it doesn't give you nice or physical results. This happens sometimes. particularly at very high frequencies. So the assumptions in cable constants. So Jean mentioned about MOMSO. So I think we'll solve this problem very soon. I mean, this is not the thing that happens all the time, but let's say 2% of cases, 3% of cases, because of cable constants, you may have some issues. But with the introduction of MOMSO and other improvements, this, I think, will be solved very, very soon. So what did we do with the fitter? We rewrote the fitter, and we used the fast-weighted vector fitting technique. I don't know, have you heard of vector fitting technique or not, but it is a powerful technique. But since we did the formulation in MATLAB, we had to use a fast routine that vectorizes everything. So Jean showed you click on the wideband model, you wait for the MATLAB to open, but then the fitter is very quick. Why? Because in MATLAB, normally it is not very quick, right? But we vectorized everything, so it is fast. And also we use this weighting approach, our approach, so we use less poles, and also we do optimization regarding the time delays. We little bit perturbate them to minimize the errors and to minimize the number of poles. These are all important features of the fitter. And also we apply a frequency-dependent cable model. This is called cable correction in the new model. So, for cases with coaxial cables and several conductors, this is a very good solution. Because if you have several conductors, the universal line model considers all model contributions in the same mathematical equation. And this becomes an overdetermined, so rank-deficient system, so you don't get good results. But with the frequency-dependent cable model, we don't have that problem. We fit each model contribution separately. So this works for 50 cables, 100 cables. There is no such tool right now, professional tool or commercial tool available except this one. So it is a nice feature to have. And we have DC correction. And frequency partitioning, because, for example, you have a very short line. If you have a very short line, and if you take a frequency band up to 1 megahertz, you won't see the propagation modes decaying, you know? They will be flat, because it is short. So the waves don't decay. You don't have enough attenuation or whatever. It is, in that case, well, you need to extend your frequency band. But when you extend it, the fitting becomes complex. It is stiff. So what you do is basically, okay, in that case, we need another solution. In that case, what we do is we have this DC correction option. So the DC part is separated, and the rest of the band also is fitted individually. So then we combine the solutions, and then this way we can really handle short lines in wideband model. This was not possible before. So there is another detail about the eigenvector switchover, but I won't talk about it. It's just regarding transformation matrices and eigenvalues, but not very important. And also regarding the time domain model, we changed everything in the time domain model. So we don't use trapezoidal anymore. We are using the exact solution, considering that the input is piecewise linear. I think this is the first in EMTP world, or the electromagnetic transients world, that you have the exact solution implemented in a tool for the line models. This has many advantages. So we don't see ringing waveforms. And we have better precision than Euler backward, whatever. And also there is this feature of, because you have propagation function, in time domain, of course, you find the solution with convolution. It is, again, in the theory books and everything. But the problem is you have interpolation errors. Why? Because you need the past values, right? The conditions at one end of the line depends on the conditions actually at the other end, but with a time delay, right? This is what propagation function does, the convolution propagation function. You take the conditions at the other end, you apply propagation function, and you get your conditions at this end. This propagation function, of course, has delay, attenuation, so on. But this thing is So you need past values, right? Basically, you need past values. But the time delays are not integer multiples of your time step. So if you go to EMTP's buffer, history terms, it won't give you the exact past value. What do? You interpolate. You know, it is, so basically, however, what we do here is we use a two-step convolution. So I have 2 points, and I need the value in between. I do convolution to do that value in between, and I do a second convolution. Really helps, really helps. It is also a great improvement in my opinion. So I'm proud of time domain. It is a time domain I don't think anyone will touch ever. Maybe there may be a bug or whatever, but the solution-wise, I don't think there is a better solution. It is, we somehow finished that field. It is, but the wideband filter, there are still things to do. It is, there are still things to do. So some other details about the time domain model. Initialization, for example, because the existing solution based on pi equivalent, I just discarded that solution because it was creating mismatch. So I built the nodal admittance matrix using propagation function and characteristic admittance, their frequency domain counterparts. So this gave me a perfect transition from load flow or from steady state to time domain. And of course we used object-oriented structures, so we don't have this 5-dimensional arrays. So you may realize, yesterday I saw a German researcher, he said me that I use wideband model, he has the new version, and he said, it is faster than constant parameter model. I said, there's something wrong. It cannot be faster than that. But I think he had this impression because it is faster. Because in constant parameter, you don't have these transfer functions or whatever. You have just constant parameters. Because in frequency domain, I mean, in wideband model, I do convolutions, right? Because you have a function in frequency domain. In time domain, the counterpart is a convolution. The multiplication of 2 functions in frequency domain, it is the convolution of 2 functions in time domain. So what is the multiplication? Your input current multiplied by the propagation function, and so on. I think he had this wrong impression, but the thing is it is 2 times, 3 times faster. It is really fast. And also regarding the memory allocation, because it had limitations in terms of number of conductors, the universal line model, so we don't have this limitation anymore. And I do not allocate memory based on maximum number of conductors or whatever. I allocate based on what you have. You have a 3-conductor, I do allocation like that. It's dynamic allocation. So this saves you in certain cases 90% memory. Very good, very good. Another thing. And here, for example, a simple case, DC line cable case. You have a DC line and you have a cable. And as you see here with the DC correction, the black line is the new model. We get perfect DC response. You know, it is really, we have no oscillations, whatever. We get perfect DC response, yeah. This is, actually my student Miguel studied that case. And you see, because thanks to DC line cable, thanks to DC correction, this is a nice case showing the importance, you know. Because I do partitioning and I take care of DC frequencies separately, and I apply a correction term, whatever. I think this is very good for studies with AC-DC lines or HVDC lines, hybrid configurations. And of course, the stability. It is because I do partitioning, I get nice parameters. My system of equations does not get ill-conditioned. So these are the advantages that I have. Here, another example, I have 12 conductors. With universal line model, unfortunately, if you have 6 cables or more, because of all these dynamics that I mentioned, you will end up with some problems. So right now it's not a problem. Here I see that the eigenvalues of the nodal admittance matrix are all positive. What does it mean? It means that your resistances are positive. the nodal admittance, your resistances are positive. So it means that you don't have a negative resistance. So you're passive. However, the time domain solution is exploding. Why? Because the reason is because of the numerical integration errors. But now we don't have this anymore because, well, here it is interesting. So we are applying cable correction in this case, and we get a stable result with the existing time domain model. But with the new time domain model, not only stable, but also smooth. You see? This is the correct answer. This is not the correct answer here. This ringing here is not correct. It is because of trapezoidal or discretization of your equations. But here it is the exact solution that we implemented. So also another advantage is, for example, there is a case. What you do when you model a line, for example, or a cable, if you have a certain time you need to choose your time step based on time delays. So your time step should be less than the time delay, right? Because otherwise you won't be able to catch the traveling waves. So what we do is usually we take 1/10 of the smallest time delay as our time step. Here the minimum delay is 6 microseconds, so I take 0.6. This is the new one, this is the old one. You see the new one is good. I take 1, I exaggerate, the old one goes nuts. The new one is still performing, it is behaving. And I go to 2 microseconds, which is crazy because minimum time delay is 6. The old one goes nuts again, but the new one is still behaving. It gives you some result. So this is nice in a way. And the multi-conductor case, for example, this is not a problem anymore. For the fitting, it may take some time. But this is offline because you have too many conductors. I need to take care of all of them, and I need to find poles, residues. If I apply cable correction, it takes more time, obviously. Okay, so, but this is not a problem anymore. So regarding time delays, we optimize the time delay routine so we don't get any more delays. That gives you speeds faster than speed of light. So. So reasonable time delays, and also the initialization. In this case is exaggerated, but this is the new case. For example, I initialize from steady state and I go to time domain. My frequency domain counterpart matches the time domain in the new code. It is perfect. I don't see any things like that anymore. It is, we tested many cases and it was always perfectly initializing, unless, of course, there is another reason for explosion or numerical problems. So the conclusions, we can solve many problematic cases that could not be solved before. And we have more options to provide the user with a stable model. And we have less interpolation and integration errors. But I'm sorry, with the fitting is complex and you may still need to play a little bit. For example, in cases if you have problems, you may need to play with your number of samples, frequency range, or fitting error criterion, time step, grouping option, DC correction option, and the cable correction option. So these are the options that we provide. If there is a problem, you can say, okay, it's a short line, maybe I increase the frequency band, and then since I increase the frequency band, it's a good idea to apply DC correction as well, so partition the band and so on. These are particularly for short cables and lines. Otherwise, if you have a 50-kilometer line, I don't think you'll ever need it. The default parameters will just work. I mean, this is for 98% of the cases. So in future, we'll find a solution for short lines. It will make it easier, without user intervention. We will detect it automatically, and we'll do the corrections ourselves. So future work is, still we may have some cases with passivity problem, so we'll apply passivity enforcement. And we'll have the constant transformation matrix option probably. So you won't need FT line anymore. Everything will be wideband, just one model. If you want a faster model, you say just, okay, I don't want frequency-dependent transformation. This is also called J-Marty model sometimes, but but in EMTP, the wideband model is not called Kocar or Maseredian model. So this model is not called also with a name. It is called FT line, wideband line. So, yeah, I wouldn't argue if you change the name to, yeah, it's... Okay. So maybe we'll have also this variable time step option and also other things we are working on, but these are research topics. And we'll have also adaptive line models maybe, so the line model will be intelligent and it will switch to constant parameter model if you are in steady state. And then when you have a switching, it will switch back to frequency domain, wideband model. Regarding passivity, we have some solutions, and so we are considering residue perturbation of YC and H at the same time. No one has done before. We checked the solutions in the literature, they don't work. So, but we have our in-house solutions and they are very promising. Some people suggest playing with the G parameter. We could have done that, but we don't like the idea of playing with parameters to improve the model. The parameters should be as they are. We should not play with the input parameters. So this is what we think. And I added a slide on the my working group here, but I'm not, so next year you are invited. The working group on field measured over voltages. It is an interesting work group. You can see the also performance of our wideband line models in this work group. There are challenging cases, field measured over voltages that you cannot reproduce in EMTP, or you overestimate. We solved these cases, we understood the reason behind, and we perfectly matched these cases. This is particularly for lines 230 kV and below, so you don't have any mitigation for over voltages like surge arresters or closing resistors. But this is just an invitation for next year. Yeah, this is the end of my presentation. Thank you very much.
Thank you. Any questions? We have time for one question. Yep.
When you apply the vector fitting technique, we know that vector fitting is a pole relocation technique, right?
Yeah, yeah.
So how do you decide how many iterations you apply in this pole relocation?
You increase one by one and you check.
So you calculate poles, one iteration more, you calculate also residues, and you check the RMS error?
Exactly, exactly.
So it's not fixed, the number of iterations?
No, it is not fixed, yeah, yeah.
Okay, and one more quick question about passivity. Do you check passivity point by point according to the frequency vector that you choose?
Yeah.
Okay, because there also exists this Hamiltonian test.
I know.
So it's not applied
No,
yet.
no, it is not applied. Maybe not.